Welcome to the Podkey summary of Build Real-Time Neural Rendering Pipelines with Metal from WWDC 2026. This week's theme is Apple's graphics stack getting a lot more comfortable with neural tricks and doing it in ways that feel practical instead of sci-fi demo only. The big ideas are a very usable MetalFX denoising path for live viewports, a handful of details that make or break image stability, and a broader push toward tiny neural networks running right inside shaders. And when you zoom out, the through line is pretty clear. Apple Silicon is making real-time rendering, denoising, tone mapping, and even on-the-fly training start to live in the same neighborhood. One of the more immediately useful pieces here is MetalFX as a combined neural upscaler and denoiser that drops straight into a Metal command buffer. The pitch is simple and kind of appealing. If you build rendering tools, you can feed it the rendered image, plus auxiliary buffers like diffuse albedo and depth, and get back a much cleaner final image, even if you only traced a single sample per pixel. That matters because single sample rendering is fast, but it usually looks like the image is held together by static. What makes this notable is that it's tuned for the low latency reality of interactive viewports on Apple Silicon. So developers aren't being asked to bolt on some giant offline pipeline just to clean up noise. Minimal code changes, interactive frame rates, cleaner previews. That's the kind of sentence graphics programmers actually like hearing. If you only remember one implementation detail from the denoising side, it's probably this. Diffuse albedo carries the strongest signal for the denoiser out of all the auxiliary inputs. So if that albedo buffer is noisy wrong, or just not representative of what should land on screen, the denoiser is basically being asked to solve a puzzle with bad clues. Maxon's recommendation is very grounded. Build debug views for every input, and use GPU captures to verify that the albedo really matches the intended final screen appearance before it goes into MetalFX. That's one of those boring-sounding tips that usually saves a lot of pain later. There's also some nice control over parts of the image that don't actually need denoising. For things that are already noise-free, like particles, fog, volumetrics, or the sky, the transparency overlay input tells MetalFX to just upscale and composite them instead of trying to denoise them anyway. That avoids wasting work, and it also avoids the weirdness you can get when a denoiser starts fixing things that were not broken. Then there's a denoiser strength mask, which works per pixel from 0 to 1, so you can decide exactly where the filter should back off or go full strength. That gives artists and engine developers a more precise way to leave delicate areas alone, especially skies and other smooth regions where overprocessing tends to show up fast. The other big quality trap is motion vectors. MetalFX depends on accurate dejittered motion vectors, and even subpixel jitter can shift those vectors by up to a whole pixel, which then shows up as shimmering along edges once temporal filtering gets involved. The fix is specific. When computing motion, you subtract the camera jitter deltas from both the current and previous frame projections. And if geometry is moving or deforming, you can't fake it. You need the previous frame world position stored so you can generate true per-pixel motion. This is one of those areas where the result either feels stable and polished, or it feels haunted. Beyond denoising, there's a really interesting shift in tone mapping and color processing. Instead of building a long handcrafted chain for tone mapping, color grading, and film emulation, the idea here is to train a single neural network on HDR images, so it learns the whole transformation in one pass. The HDR net-style setup works on a downsampled image first, computes global and local descriptors, and then applies learned affine transforms over 16 by 16 tiles with edge-aware filtering. In plain language, it learns how to remap color and brightness with both scene-wide context and local sensitivity without smashing edges or flattening detail. That's appealing because it can replace a pile of individually tuned stages with one learned operator, while still producing high-quality tone-mapped output. Then there's TensorOps, which may be the most quietly wild part of all this. TensorOps lets developers put a tiny MLP, just a few thousand parameters, directly into a metal shader and run inference alongside normal compute or rendering instructions. So this isn't only about dispatching a giant model somewhere else. It's about little scene-specific networks living right in the rendering path. Because those networks are small and tailored to the task, they can be trained on the fly with just a handful of frames instead of needing some huge generalized dataset. That changes the flavor of machine learning in graphics. It becomes less about universal AI magic and more about solving a narrow problem, right here, right now. A concrete example is dynamic illumination from a skybox. The model can run inference each frame, compare its result to an analytical sky solution, backpropagate the error, and update itself continuously as the lighting shifts through a day-night cycle. That kind of online training loop only works because TensorOps can do both forward and backward passes on chip, all inside the rendering command buffer, which means the learning process stays local to the graphics pipeline instead of constantly bouncing out to some slower, more disconnected system. Underneath all of this is the execution model and the silicon itself. When a compute thread group owns the full matrix multiply, TensorOps can allocate a cooperative tensor in shared thread group memory. So you avoid expensive trips back to main memory. Using SIMDAC group execution means all the threads can collaborate on the same tensor operation, which is exactly what you want for the matmul and activation work inside each MLP layer. And on the chip side, Apple's M5 and A19 Pro GPUs include a dedicated neural accelerator that Metal4's ML command encoder and TensorOps APIs can target directly. That's what makes the whole story hang together. Hardware-level acceleration for big offline models, for tiny in-shader networks, and even for per-frame backpropagation without clogging up the graphics pipeline. Taken together, it opens the door to neural rendering features on consumer devices that would have sounded pretty unreasonable not that long ago. So the practical takeaway is that neural rendering on Apple platforms is getting less ceremonial and more everyday. Cleaner one-sample previews, smarter tone mapping, tiny trainable shader networks, and hardware that can keep up with all of it. That's a pretty solid week in graphics. This episode was generated by Podkey. Create your own at podkey.fm.